In this video, we will talk about the second derivative test. So let me begin by stating what the test says, and then we'll do an example. Okay, so the second derivative test says if c is a critical number of our function f, and so there's three cases. So in the first case, if we take that critical number and we plug it into the second derivative, so that's what we're going to be doing in all of these. So we're going to look at what the second derivative is when you plug c into it. So we'll look at that in all of these. And in the first case, when we plug c in, what if we end up getting a positive number? So what if the second derivative at c is positive? Well, that means that our function is sort of concave up at this point. Then it turns out what happens is that f has a, so what I'm going to do is I want to motivate the answer by drawing a picture. So I'm going to draw a graph, and I'm going to draw a point here where c is, and I need this to be a critical number. So wherever the point is on the graph, that needs to be a critical number. So for it to be a critical number, that either means that the first derivative is 0 at that point, which would mean horizontal tangent line. So that might mean something like a flat, it's perfectly flat like this. Or critical number could mean that the first derivative is undefined. And that could mean a sharp corner. It could mean a sharp corner or something like that. But if the first derivative is undefined, then every other derivative after that will also be undefined. And I'll briefly talk about the reason why for that. But if I had the graph of a function, and there was some value like 2, and my function was undefined at 2, that means there's no point there. So maybe my function is going along, and there's got to be no point at 2, so I have to draw an open circle. And then maybe even on the other side, maybe it just continues onwards like this. So maybe my function looks like this, and it's undefined at 2. So if f is undefined at x equals 2, then if I talk about the derivative, well, the derivative is asking what's the slope of the tangent line at 2. But if there's no point there, then I can't even draw the tangent line there. So f prime of 2 would be undefined. F prime of 2 is also undefined. And for the same sort of reason, if we were to keep going and take more and more derivatives, all of those other subsequent derivatives would also be undefined. So returning this back to our discussion here, if I had a sharp corner could be a critical number, because that would correspond to a place where the derivative at c is undefined. But when a function is undefined at a value, that means its derivative, in this case the second derivative, at that point is also going to be undefined, for the same reason as I just talked about in this graph with this hole up here. The second derivative is also undefined. Okay, so I'm just going to put this in a little bubble here. So in case 1, it's telling me that the second derivative is positive. And if the second derivative is positive, that means the second derivative is defined. And if the second derivative is defined, it couldn't have been a situation where the first derivative is undefined. Because if the first derivative is undefined, the second derivative is also going to be undefined. But here it's not. Okay, so I know that was a long kind of digression, but it's important for me to talk about all of those sort of subtle points, because we're really aiming to master this content. Okay, so, alright, so I can't have a sharp corner. It's got to be sort of flat-ish. And when the second derivative is positive, that means my function is concave up. So my function's got to be concave up shape, so upwards U shape, and it's got to be perfectly flat at c, because I'm saying it's a critical number. And just by looking at this now, I can see that f has a local min. A local min at x equals c. So if I know that a value is a critical number, and I plug it into the second derivative, and the second derivative gives me a positive value, that tells me my original function is sort of concave up. It has this upwards U-shape. And if it does have that upwards U-shape at this critical number, there's going to be a local min. Okay, so the second condition is, well, what if the second derivative is less than 0? What if it's a negative? If it's a negative, that means, our original function is concave down. So then f has a, and again, I'm going to draw the picture. I'm going to draw the picture here. So I'll draw my critical number c. I like to draw the picture because I personally don't have this second derivative sort of memorized. I just know what the picture is going to look like in each case, and I can visualize it, and that helps me determine, oh, is it a local min, like case 1? Or is it going to be like case 2? So in case 2, at my critical number, it's going to be concave down. So that's going to be something like this. It gets perfectly flat at my critical number, perfectly flat, and then it concaves down the whole way. Well, in my picture, I've drawn it concaving down the whole way, but I mostly care about is it sort of concave down right at C. So in that case, f would have a local max. F would have a local max at x equals c. Okay, so there's one final possibility. We've talked about the second derivative being positive in case 1, that's concave up, or the second derivative being negative in case 2, and that made a concave down graph. But we could also have the second derivative be 0 or be undefined. So if the second derivative is 0 or it's undefined, then the test, the second derivative test, is what's called inconclusive. So when we say it's inconclusive, that means there could be a local max, a local min, or neither at x equals c. We just don't know based off of the second derivative test. And if that happened, well, then we'd have to use the first derivative test. So remember, the first derivative test was the thing with the number line for the first derivative, where you figure out where your function is increasing and decreasing. Okay. So first derivative test, remember, we talked about this in section 5.1. This was the first test we had to figure out whether our critical numbers were local mins and local maxes. All right, so let's do an example. So in this example, we have this function. So you might remember this is the same function that we looked at in the last video, this 5th degree polynomial. And I want to use this second derivative test to classify the critical numbers as local maxes, local mins, or say the test is inconclusive. Okay, so we are going to need to find the critical numbers. So let's take the first derivative. The first derivative, we did this in the last video, but it's going to be x to the 4. That's from bringing the 5 down. We don't need quotient rule for this. Remember, as we talked about in the last video, this is 1/5 x to the 5. So I don't need quotient rule for that. In the same way, I don't need quotient rule for this next term. The derivative of that is going to be minus 8x squared, and the derivative of the plus 2 is 0, because that's a constant. Okay, so to find critical numbers, we have to find where f prime of x equals 0, or f prime of x is undefined. F prime of x is undefined. So the derivative is never undefined, so this never happens. Because I don't have to worry about, my derivative is a polynomial, so I don't have to worry about a denominator being 0 here, or there being a square root of a negative number, or the types of things that can make my function undefined. Okay, so let's figure out when the derivative is equal to 0. Let's set x to the 4 minus 8x squared equal to 0. And I can factor an x squared out of these terms and be left with x squared minus 8. So from the x squared, I get that, from setting that equal to 0, I get that x equals 0. Or from the x squared minus 8, we get that x squared minus 8 could be 0. And if we rearrange this, if I move that 8 over and square root both sides, we'll get x equals plus or minus square root of 8. Whoops. Plus or minus square root of 8. Okay, so the other thing that we have to check to see are these actually critical numbers is looking to see if the original function f is continuous at these values. So the original function is a polynomial, so it's going to be continuous everywhere. So f is continuous everywhere, but specifically at these values. So the critical numbers are these values. They're 0, root 8, and negative root 8. Okay, so let's apply the second derivative test to these values. So what we need to do is we have to plug the critical numbers into the second derivative. So let's recall what the second derivative was. Let's recall that the second derivative, we had actually written it in factored form in the previous video. It was 4x times x minus 2 times x plus 2. And it's just a little bit easier to plug into factored form to determine whether the whole thing is going to be positive or negative. Okay, so let's do that for each of our critical numbers. So let's do it for root 8. If I plug that in, we'll get 4 root 8 times root 8 minus 2 times root 8 plus 2. Okay, so 4 is positive, root 8 is positive. What about root 8 minus 2? Well, I know that root 4 is 2. So that means root 8 must be bigger than 2, because it's bigger than root 4. So root 8 minus 2 is going to be positive. And then root 8 plus 2, well, that's definitely positive. Okay, so all these positives multiply to give me a positive number. And that means our function, our original function, is concave up. That means our original function is concave up at this point. So if I don't remember the second derivative test and what it says, this is where visualizing the graph can be helpful. So if I draw some axes, I need to draw my function to look concave up at my critical number. So let's say this is root 8. So I got to make it a critical number so it gets flat there, and then concaving up. And now I look at the graph and I ask myself, okay, local min or local max? And that's definitely a local min. So there is a local min at x equals root 8. And if we were to check this with the second derivative test and what it says exactly this. When the second derivative is positive at our critical number, then we have a local min there. Okay, but again, having this visual idea of what the picture looks like helps us not have to memorize. Okay, so now let's plug in the other critical numbers. So let's do negative root 8. Okay, so we'll get 4 times negative root 8 times negative root 8 minus 2, and then negative root 8 plus 2. So 4 is positive, and then after that we have a negative times a negative times a negative. So overall 3 negatives multiplied is going to give me a negative. So this is concave down. So I could draw a picture to help me. So let's draw a picture. So at negative root 8, and again, I don't really know how high up or down my graph is. This is just for a rough picture. But at my critical number, I got to make it look concave down. I got to make it look concave down. And it's flat there. It's flat at negative root 8 because of our discussion at the beginning of this video. It's a critical number, which means at this value, my graph is either going to be flat, so horizontal tangent line, or it could have a sharp corner or a cusp or that sort of thing that makes it not differentiable. But if it was like that, if I did have a sharp corner or something, well, then the first derivative would be undefined. And then that would force the second derivative to be undefined. But that can't be true because we just got that the second derivative is negative. So that's how I know that this critical number is flat. It's not something like a sharp corner. Okay, but looking at my picture, now I can see, oh yeah, this is a local max. Local max at x equals negative root 8. Okay, one final critical number to check, which was 0. Okay, so let's take our second derivative. Whoops, second derivative. Plug 0 into it. So if you plug 0 into this, you'll get 4 times 0 times some stuff. But anything times 0 is just 0. So this is 0. And the second derivative test says, okay, when your second derivative is 0, then our test is inconclusive. So for the purposes of our example, we get to stop here. Because this example just said, let me go back to it. This example just said, use the second derivative test to determine whether the critical numbers are local maxes, local mins, or say that the test is inconclusive. If instead the question had said, just classify the, if it didn't say specifically, use the second derivative test. If it had said just determine whether the critical numbers are local maxes, local mins, or neither, and I had decided to use the second derivative test to do this, if I run into a situation where the test is inconclusive, we would need to use the first derivative test. So we would need to use the first derivative test. Okay, so that's one of the negatives of the second derivative test. The fact that you can run into a situation where it's inconclusive and then have to use the first derivative test at the end of it. Okay, so I'm going to end this video with just a comparison of the two tests that we have. First derivative test and second derivative test for checking for local mins and local maxes. With the first derivative test, the key positive is that it always works. There's no situation where you're going to run into like an inconclusive case like you do with the second derivative test. And that's the main drawback or negative of the second derivative test. It does not always work. Because it can produce inconclusive results. Inconclusive results. Okay, but there are drawbacks to the first derivative test as well. The main drawback is the first derivative test involves a sign chart. And the sign chart is sometimes tedious to make. Sometimes tedious to make. You have to select test points, plug all those test points into the first derivative to see if it's positive or negative, and sometimes it's a tedious process. With the second derivative test, one of the key positives to it is when it does work, when it works, so when it doesn't produce an inconclusive result, it can be faster. Since there are less critical numbers, than test points. And by test points, I mean things that we get in the first derivative test that we plug in to the first derivative test, numbers in each subinterval. So these are things from the first derivative test. So sometimes also the second derivative test is just simpler than the first derivative. So it's easier to plug into the second derivative than it would be into the first derivative. On the flip side, there are some cases where the second derivative is more complicated than the first derivative. For example, if I had to use product rule or quotient rule to take my derivative, usually the second derivative is going to be even more complicated. And that's a sort of something that would discourage me from using the second derivative test. So it's important to be aware of these positives and negatives when deciding in a local max or local min problem, well, which one should I use? All right, in terms of our goals for the section, we have finished goal 3. How to use the second derivative test to test whether critical numbers are local mins or local maxes. In the next video, we are going to do an example where we are given the graph of the derivative of a function and then use that to find where the original function is concave up and concave down.